pleasure to have the first lecture of Daniel Cabarcas Jaramillo from the Universidad Nacional de Colombia in Medellin. And the title of the series of lectures will be Solving Nonlinear Equations with Linear Algebra.
All right. Well, thanks a lot. All right. Hello, everybody. I'd like to thank SIMPA and ICTP for making this possible. They have everything set up very nicely here at ICTP, and I'm glad this can happen. So if you have questions, please interrupt me. This is supposed to be a lecture and in an informal setting, and I love to have questions at the moment so that I can actually address them immediately. That goes for the people who are in Zoom and also for the audience here. Please ask me if you have questions. If I don't see them right away, maybe you can even open the mic. No problem. I'm planning to have, it's supposed to be a 2-hour lecture, so I'm planning to have a 5-minute break in the middle, so that it is not that long, and I can take a short break, and everybody can take a short break. All right, so let's start. Solving nonlinear equations with linear algebra. So solving systems of polynomial equations is a very useful tool. It has many applications in science and technology. The theory was developed in the 20th century, in the 30s and the 60s by people like Macaulay and Buchberger. And later on, in the 80s and 90s, the people like Lazard and Faugere reframed the problem in linear algebra terms, which made possible improvements in the way the equations can be solved. So it especially made it possible to solve it much more efficiently and to better understand the complexity of the problem. And so I'm going to be talking today first of the background on the basic of the classical way to solve systems of polynomial equations, and then I'll make that connection with using linear algebra. Eventually, I will talk about some of the most advanced algorithms to solve systems of polynomial equations, and also about the complexity of solving those equations. So the course will cover first a short motivation, then I'll talk about Groebner basis and elimination theory, like the classical stuff. Then I'll talk about linear algebra to compute Groebner basis, with emphasis on the algorithms, on the connection with linear algebra. And finally, I'll talk about CCGs and the complexity of Groebner basis computation. This will take the 4 sessions. So there's 1 session every day from today until Thursday. Today I'll probably cover the motivation and Groebner basis. Maybe I don't get to elimination theory, and then next lecture I will take from there. So motivation and Groebner basis. That's the outline for today. The classical algorithms, the classical theory, because I need to set up the theory, the basics, so that we can actually cover the connection with the algebra. All right. So there are many applications, but I actually work on cryptography, applications to cryptography. So that's the applications I actually know about, and I'll talk about a bit about this. So when I first started to work on this, there was a huge hype. People thought many crypto systems could be broken using Groebner bases. And this started probably in 2002 with this paper by Courtois and others, where what they did was, in a way, very simple. They took a crypto system, and an attack on that crypto system, they simply reduced it to problem solving a system of polynomial equations, right? And they claimed that it was possible to attack the system, just solving a system of polynomial equations over a finite field, right? And what was really interesting is that you can do this with many crypto systems. Basically, every crypto system can be written on a finite field over a finite field, and you can transform it to a system of polynomial equations. Like the trapdoor can be thought as a system of polynomial equations, and you can write the problem as solving a system of polynomial equations. The attack can be reduced to solving a system. And they thought it was maybe possible to even break things like AES. AES is the encryption scheme that is used for most of the communications we do on every platform. And people were very hopeful, and there were the algorithms to compute Groebner bases were getting better. So there was a lot of hope, but this did not really materialize. So the truth is that there was a good reason why AES is secure, and just writing the system on a different language, the language of polynomial equations, was not going to make much of a difference, right? So this did not happen, but two important things did happen. Many people started thinking about how to improve the algorithms to solve polynomial equations, and also on the side of public key cryptography, there was also emerging a different kind of crypto systems based on polynomial equations. And it was very important to understand the complexity of solving systems equations. So one of the important breakthroughs was this paper by Faugere and Juve from 2003, when they broke HFE. HFE is a crypto system based on polynomial equations, proposed by Part.1 in '96, and by doing by computing more efficiently the Groebner bases, they were able to break it directly, solving the system of equations. It was a huge system. It thought it was not possible, but it was not a completely generic system. It had a lot of structure, and the algorithms to solve equations was able to take advantage of that structure and actually solve it efficiently, or polynomially. Since then, there's been a lot of developments, and more recently, the scope of the applications of these attacks have increased. For instance, in this paper by Buchberger and others, we were able to break some schemes that are based on code-based cryptography, that are based on coding theory. And this is not that easy, that direct application of solving equations, but it can be reframed, it can be reduced to a subsystem of equations. And it was possible to break it using Groebner basis. Or actually, not Groebner basis, it's algorithms to solve equations related to Groebner basis. So finally, I recently got involved in a project related to hyperelliptic curves, and I don't know much about this, but it's difficult to actually given a curve to understand the group and to get the structure of the group. And one thing we always want to do is have the L section for some L, so two sections. Get the 2-silo group, the 3-silo group, or get part of the structure, and this can be done. There are ways to do it if you know, for example, how to take square roots or how to take roots. And it turns out that for the 2-silo group, there's a very easy way to do it, very classical way to do it. But for larger L's, what you can do is set up the problem as solving a system of polynomial equations. So you have information about the generators, and you try to find the generators by setting up some equations over a finite field or over a certain extension. And that's also interesting. You eventually have to solve a large system of equations, and you have to do it several times to get those generators of the silo group. So that's also. And of course, there are many more applications. There are applications to computer-aided geometric design. When you are using curves or surfaces to design, you want to have two kinds of descriptions of the curve. You want to have a parametric description so that you can draw it, but you also want to have a implicit description to know when what points lie in the curve, to given a point, to know if the point is the curve or not. And this theory of Groebner basis allows you to go back and forth. Not perfectly, but it can help in this getting the implicit or the parametric form of the curve or the surface. In robotics, you get usually you have, let's say, a robotic arm, and you have a point in space, and you would like to know what configurations of the robot arm put the arm of the arm of the joints, actually put the arm where you want at that point. What are all the different configurations of the joints of the robot that actually, and this is actually a question of solving a system of polynomial equations again. So that's also very common. Then I even put there something of celestial mechanics, and again, I'm not an expert on this, but it turns out that when I was doing my master's in computer science, my advisor who was working on this, and this is how he got into Groebner basis, and I thought it was interesting to point out to this now that I'm here at the ICTP. So the n-body problem, it's hard to get actual solutions to, so the exact solutions to the n-body problem, except under very specific, very contrived circumstances. And there are certain configurations that are stable somehow, and it's interesting to look for them, to find those configurations of the n-body problem. And to do that, one way is to use systems of polynomial equations. These things are called central configurations. And yes, you can also use Groebner bases or solving systems of polynomial equations to try to find those configurations of the n-body problem. All right. Are there any questions?
The RSA system,
Are they?
The RSA system.
RSA?
Yeah, factorizing the numbers.
Probably yes. I mean, in theory, yes. So any function over a finite field can be written, can be expressed as a polynomial equation, as a system of polynomial equations. But in this case, I don't think it's really a useful one. And there's no point on doing this. It's you need much more structure to be able to take advantage of this. It's yeah, I mean it's the obvious one if you want. So you want the product of two numbers to be the other one. Right? All right. Any other questions, comments? Okay. Let's move on. So we're going to be interested on doing this over a finite field. So capital K is going to be a finite field. Of course, you can work over any other field, but there's so solving over the complexes is much easier in a sense. You have other tools. Over a finite field, you're a little bit limited, but on the other hand, it's finite, and you can actually list the solutions. You can list the elements. You can do other things. In cryptography, the applications are usually over finite fields. So that's why I'm going to be working on finite field. And capital K. So and we're going to have we're going to be working with a ring of polynomials in n variables, x1 through xn, and going to be representing that for simplicity just as x and kx with a bar on the bottom to represent the vector variables. Then we're going to be looking for solutions on the affine space over K in affine space. Sometimes it makes sense to do it over a projective space, but for the applications, usually what we want is just solutions on the affine space. And what we want is to find all solutions over K to the n to a system of polynomial equations if 1 to fm equals 0. That's the problem. Now, there are some sub-problems that come up from that initial problem. Is is there a solution? Is there a solution? Can we list the solutions? So since we're a finite field, we list them. Have a way, can we parameterize? Can we have a parameterization of that solution space? What is the dimension of that solution space? Right? It could be just isolated points, or it can be kind of a curve or a surface. I mean, we're talking about a finite field, but still, you can talk about the dimension of the solution space. And then, what is the computational cost of doing this? Right. So, in cryptography, we are interested in solving very, very large systems where the complexity is critical. We want to be able to solve very large systems of polynomial equations. But here's a tiny one, just to illustrate what we're doing. So there's two equations in two variables, x, y. We're looking for solutions in the Galois field 7, GF7. So here is how the classical way to solve the systems works. So by doing operations on those, certain operations on those equations, you can manipulate the equations algebraically, and you can rewrite the system as this. And trust me, it's the same solutions. I just manipulated the system somehow, and I come up with this one that is just written in a different way. Right? It's the same system. It's derived from those ones. So these equations come from those on the top. And if you look carefully at this, the second equation only involves y. And that is nice because then we can factor that second equation to find 3 roots. In this case, there are 3 roots over GF7. Y equals 6, y equals 3, and y equals 2. Over the algebraic closure, that there will be 4 roots, but in this case, there are 3 roots over GF7. And then what we can do now is take each one of those and plug them back onto the first one. And if we plug them back into the first one, for each one, we're going to get a linear equation on the x. When we plug, if we plug in y equals 6 on the first equation, we're going to get an equation only on x. And then we can solve for x. And we do that with each one of those. And we get the x component that corresponds to that y component. So when you plug in y equals 6 here, you can solve for x and get a 1. And so on. Each one of those. How can a sum, so Barut asks, how can a sum of positive numbers give 0? Well, this is over GF7. So let's say we're doing here modular arithmetic, everything modulo 7. So it can, so 6 plus 1 is 0, right? Or 3 plus 4 is 0, right? So that's the idea. That's how this works in general. I'll go back to that in a minute. And here's the notation, the definitions we're going to be using. So V of F1 through Fm is the affine variety, which is the set of all solutions, the set of all tuples that satisfy the equations. Then the angle brackets I'm going to use for the ideal generated by F1 through Fm. You can also talk about the variety of the ideal, and that would be denoted by V of I. And this is the set of all tuples that are satisfied for every polynomial in the ideal. And then you can talk about the variety of the ideal of the variety, which is the set of all polynomials that vanish on every point in the variety, or in any set actually. Next, we're going to need a monomial ordering. So a monomial ordering is an order on the monomials of the polynomial ring, and that we need that ordering to be a total order. We need it to be a well ordering, and we need it to preserve multiplication. As an example, here we can use a lexicographic order, or we could use a graded lexicographic order, for example. Once we have an ordering, we can talk about the leading term, the leading coefficient. And we will be also using degree and multi-degree. And just maybe I'll have a tiny little example here just to get everybody on the same page. So let's consider a polynomial in two variables. Let's say x, 2 y. Polynomial I ordered, so these are two variables x and y. I'm considering x to be larger than y, and I'm ordering the terms, the monomials in the lexicographic order. So x is larger than y, and then this one, x squared, is larger than xy, larger than x, larger than y squared, larger than y, larger than y. The degree is the sum of the exponents. The multi-degree is going to be, in this case, a pair. So, for example, it's a pair of the degrees of each one of the variables. So the multi-degree of x squared simply to 0 is a tuple of the degrees of each variable appearing in that monomial, and the multi-degree of this one would be 1, 1. We can define the ordering on the tuples, and then the ordering of the on the tuples is gives us the order of the monomials. And in this case, 2, 0 is larger than 1, 1 in the lexicographic order. the greater lexicographic is doing the same, but it first orders according to degree, and then it orders according to lexicographic order after the order of degree. So for example, here, X, which is 1, 0, in lexicographic order, is greater than, sorry, this is greater than, it's greater than 0, 2 in lexicographic order. But in greater lexicographic, the order will be inverse because this one has degree 2, and we're ordering first according to degree. The leading term of the polynomial is the term of higher order, which is, it has the largest order. And then you also can talk about the leading coefficient and the leading monomial, which is the coefficient of the leading term or the monomial of the leading term. That's the language we're going to be talking about. Hope it's enough. So now, what is the roadmap for the example I showed before? What is it that we do? What are the steps? So how to find a variety? If we had a sort of echelonized basis for the ideal, and I'll be explaining what I mean more carefully about echelonized, but a nice basis in a sense, where the last equation, it's only written in the last variable or something similar. If we had an echelonized basis, then we can solve for the last variable by solving a univariate equation. We can factor it to get solutions for the last variable. And next, for each one of those solutions of the last variable, we can substitute them back in the other equations to extend these partial solutions to the next set of to the next variable and so on. And we can continue that way until we get to the first variable. Extend the solution by substituting back. So this is very similar to the back substitution in linear algebra, but we need something more than just echelonized in the sense of linear algebra. We need a little bit more. So how do we find such a basis? And the answer is with a Groebner basis. That's what a Groebner basis is in the Lex order. We'll see that a Groebner basis in Lex order gives us exactly what we want. And the other question is, what guarantees that we can continue this process, that we can get all solutions doing this back substitution? And the answer is the elimination theorem. This is the classic way to solve systems of polynomial equations, and that's what I'm going to be doing today, and maybe a little bit of the next lecture. Right. Any questions about the setup, about the roadmap of where we're heading? All right. first thing we're gonna need is some sort of division algorithm, and we can have a division algorithm that, just as the one with one variable, we can have one for multiple variables, and we can write it as a theorem like this. Given a monomial order and a set of polynomials f1 through fn, every polynomial in the polynomial ring can be written as a combination f equals a1 times f1 plus dot 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 up to am times fm plus r, where the a sub i's and r are in the polynomial ring, and they satisfy that no monomial in R is divisible by any leading term of the f(i)s. And I'm not going to prove that that's true, but I can do a simple example just to show how it goes. Let's do a small example. So let's say we have f1 equals xy minus 1 and f2 equals x equals x squared y plus x squared y, and we want to find the r and the a sub i's that satisfy this. And so what we do to organize this somehow, let's take f1, write them here. And we put the f up here. I'm going to be looking for A1 and A2. And I'm going to be subtracting here. So it's just like a division, just with, we're dividing by two polynomials instead of one. The difference, and so we're going to get like two quotients and one remainder. Right. So we start reducing using f1, f2. So for example, this x squared y is divisible by xy. To get them reduced, we need to multiply xy by x to reduce. To get x squared y, we need to multiply xy by x. So we need an x on a sub 1. And when we multiply x by f1, we get x squared y minus x. And then we subtract. The leading term cancels. This x squared y squared cancels when we subtract. And we end up with x squared plus x plus y. Now to get this x squared cancelled, we can use f2 multiplied by x. So again, we need an x, but now in a2. When we multiply x by f2, we get x squared plus x. And we subtract, and this cancels, and we end up with a y. Now, y is not divisible by any of the leading terms of f1 and f2, and so we're done. And what this is telling us is that x times f1 plus x times f2 plus y is the reduction of f. So f can be written as x times f1 plus x times f2 plus y. This is the remainder, which is none of its terms is divisible by any of the leading terms of f1 and f2. And you can see how this can be done in general. So I don't need to prove it. The proof is basically to follow these. And there's an actual, but there's something important here. So unlike with the one variable case, there's nothing that guarantees that we have unique remainders here. And actually, that's the reason why I actually put f not as a set, but as a tuple, because the order in which you choose place your polynomials matters. What you are dividing by first or second does matter. And it also doesn't solve the ideal membership problem, because you don't have unique remainders. You don't know if polynomial belongs to ideal or not. That's actually the algorithm. There's nothing special about it. It's basically what I did here, written as an algorithm. Take replace it here. This is not working. Oh, there. So h is going to be the polynomial you end up with. This is going to become the remainder, and you are subtracting exactly what you need to cancel one of the terms of what is left there in h, and you continue that until there's nothing else to choose to reduce. Now, the way to get to Groebner basis, one easy way to do it is through a very simple case of or type of ideals, which are the monomial ideals. These are just one type of ideals that are very easy to understand, and we can actually say a lot about them very easily. So I is a monomial ideal if it's generated by a set of monomials. So when I write here x to the alpha, what I mean is raising x to a tuple. So what I'm doing here is, I don't think I introduced that notation, but what I mean here is if we have two variables, x1 and x2, and we have an alpha, which is a tuple, let's say 3, 2. What I mean when I write x to the alpha is x cubed, x1 cubed, the first variable raised to the power of 3, times x2 raised to the power of 2. So that's what we're going to mean by this. And what I'm saying here is this ideal is generated by a set of monomials. So each one of the generators is simply a monomial. Let's do a simple example, and we can actually visualize why these ideals are so simple and nice. So let's consider the ideals. I'm going to do something with two variables, x, y squared, and x cubed, y. This is the ideal generated by two polynomials, but the two polynomials happen to be monomials. And these are very nice. We can actually, so it's not hard to prove that every polynomial in that, so the polynomials in that ideal are precisely the polynomials whose terms, whose monomials, whose terms are divisible by x, y squared, and by x, or by x cubed y, by any of those. And there's a nice way to visualize how this ideal looks like. We can do it like this. So I'm gonna put the first exponent in the x-axis and the second exponent in the y-axis. And what I'm trying to, so I'm considering tuples as monomials. So here I'm thinking of xn as the exponents, x to the n, y to the n. And I'm just trying to show the exponents here, the monomials that are involved in these polynomials, in this ideal. And so, of course, there are no fractions. It's just integers, right? So we're going to be looking at just the integers. So, for example, xy squared would be 1, 2, the tuple 1, 2, and x cubed y would be the tuple 3, 1. And so it's not hard to see that as multiples of xy squared, we can get anything to the right and above 1, 2. So for example, this one or this one, we can get from xy squared multiplying by x. And multiplying by y. Oh, the other way, multiplying by y and multiplying by x, we can get these ones. And in fact, anything in this area can be obtained by multiplying xy squared by x or by y. And the same happens with x cubed y. We can get any of these. And anything to right or above 3, 1 can be get from those. And So what we get is really this lattice. It's not a lattice. This set of points that lie in that, and they expand that direction. So what can be shown, can be proved easily, is that the polynomials in that ideal are exactly the polynomials that are written in the monomials that are presented here. So to the right and above this point, to the right and above this point. And then Dixon's lemma says that any monomial ideal is finitely generated. Of course, this one was already finitely generated, but in general, there's the set A can be infinite. Nobody's saying that A is finite, but Dixon's lemma shows that any monomial ideal can be finitely generated. It's finitely generated. Find a finite basis. The proof is not hard. I'm not going to do it here, but just to give you an idea of how it works. The idea is the following. It's by induction on the number of variables. You can do it by induction, the number of variables. So we can sort of visualize it here. You can project to one less variable apply the inductive hypothesis on one less variable to get a finite set of generators for the projection on one less variable. And then do the same on the slices above certain points. And when you put together those slices for those points exactly, you get a set of generators for the whole thing. It's a bit more technical, but it's not hard to write. Now, Hilbert-Base's theorem says that this is not only true for monomial ideals, but for any ideal a polynomial ring. Every ideal is finitely generated. Maybe I should write this because the idea of a Groebner basis comes exactly from looking at that proof. So and the idea is simple. We're going to be using Dixon's lemma. We're going to apply it to the ideal generated by the leading terms. And then when we get that, that happens to be a set of generators for the ideal. Right? So apply Dixon's lemma to the ideal generated by the leading terms of a F1. Sorry, we don't have a set of generators. We have an ideal. So let's apply it to the ideal generated by the leading terms of the ideal. That way, we get a set of polynomials in the ideal whose leading terms generate the ideal of the generated by the leading terms. These are elements in the ideal. Such that they generate the ideal generated by all the leading terms of the ideal. But we're not done yet, because they generate the ideal generated by the leading terms, but we need to show that they actually generate the ideal, right? We need them to be a set of generators for the ideal, right? So now let's show that the ideal is actually generated by G1. So to do that, let's take any polynomial f in the ideal. And let's divide it. So let's do the division algorithm of f using those GIs. So by the division algorithm, there exists H1 R such that F is the sum of the R, and no monomial in R is divisible by any of the monomials in G. No monomial in R is divisible by the leading terms of the GIs. But then f is in the ideal, and this sum is also in the ideal. It's a product of polynomials multiplied by the GIs, and the GIs are in the ideal. So R is in the ideal. And if R was not zero, if R was different from zero, and we looked at any of its monomials, then we get a problem. Then the leading term of R belongs to the ideal generated by the leading terms of the G of the ideal. But the ideal generated by the leading terms of the ideal is equal to the ideal generated by the leading terms of the GIs. And then it will be divisible by one of those leading terms. That's or so. And this contradicts that no monomial in R is divisible by any of the leading terms of the GIs. R must be 0. And we're done. An arbitrary F is in the ideal. So what is interesting, what is nice about this, and why it was important for the sake of this talk, is this condition here. We not only we had a finite basis, finite set of generators for the ideal, but we have a finite set of generators whose leading terms generate the ideal of all the leading terms of the ideal. And this is precisely what we're going to be calling a Groebner basis. A finite subset G of an ideal is called a Groebner basis if the ideal generated by the leading terms generates the leading terms of the ideal. And it's not hard to see that, looking at this proof, that every ideal, different from 0, has a Groebner basis, and that it generates the ideal. So here I'm not saying that it's a set of generators, but it definitely is. I mean, if you get this condition with elements from the ideal, you do get that they generate the ideal, as we saw here. And also, there are a few more results that come out quickly from there. You get that every ascending chain of ideals eventually stabilizes. So this is Noetherian, and so you cannot have infinite series of ideals. And you also get that the variety of the ideal is equal to the variety of the polynomials. Also from here is quite easy to see. And I'm thinking I'm going to take a pause here. I'm going to take a break. It is 4:12. We can come back at 4:20. So in 8 minutes. And when we come back, we talk about how to actually construct a Groebner basis, because this was, I didn't tell you how to construct a Groebner basis really. These are theoretical, but we're going to talk about how to construct a Groebner basis. We have to find what a Groebner basis is. It shows that they do exist. that and so the first nice property is that when you have a Groebner basis, you get unique remainders. So if G is a Groebner basis for an ideal, and F is any element in the polynomial ring, then there exists a unique R such that F is equal to G plus R for some G in the ideal, and no term of R is divisible by any of the leading terms of G. So we have this nice property that we always want for a division algorithm. We get unique remainders. And maybe I should quickly show that this is the case. It's very simple, but it's the first application of this. And we should convince ourselves that this is actually useful. This kind of basis is useful. So the existence was already shown. I didn't prove it, but it's the division algorithm we already have. So the uniqueness is the only thing we want to show. So what we want to show. And so let's suppose we don't have unique. So let's suppose we have two. Suppose F can be written two ways, as G plus R and also as G prime plus R, where G and R's and G prime and R prime satisfy both this condition here. So no term of R is divisible by any of the leading terms of G, of the Groebner basis. Then we can subtract to get G minus G prime equals R prime minus R. G minus G prime is an element in the ideal, and therefore R prime minus R is an element in the ideal. And then, but we know that the GIs are a Groebner basis. So the leading term of R prime minus R, so since G is a Groebner basis, the leading term of R prime minus R is divisible by GI, or the leading term of GI, for some I. And then notice that the leading term of R prime minus R must be the leading term of one of those, of R prime or of R. Oh, it must be a term in one of those. Is a term in R prime or in R, and because we assume what it says on the proposition that no term of R is divisible by the leading terms, then if R is different from 0, we get a contradiction. So if R prime is R prime minus R is different from 0, we get a contradiction. with the fact that no term of R is divisible by any term of any of the leading terms of G, and therefore this must be 0. And we're done. We get unique remainders. Any questions? Right. So now this R is actually can be obtained using an actual algorithm, as I showed before. We have an actual algorithm to compute this, and also now we have solved the ideal membership problem. Like here I meant F belongs to the ideal. Here, what I meant is this should be an I here. F belongs to the ideal if and only if the remainder is equal to 0. And now the next question is how to compute a Groebner basis. So the way we got to a Groebner basis was through Dixon's lemma, but we didn't show how to actually find, or through Hilbert basis theorem, but we didn't know how to, there's no algorithm to get from this infinite set of polynomials in the ideal to a finite basis. What we're going to do next is show how to actually compute a Groebner basis. Yes, I have half an hour. I should be able to do that the next half an hour. So the first thing we need is to define these S polynomials. Let F and G be non-zero polynomials. The S polynomial of F and G is this polynomial. And it looks strange, but it's something very simple. What we're doing here is multiplying F precisely by what we need so that the leading term cancels with the leading terms of G. Let me show an example. X squared plus y squared 1, and let's take G to be x1. And so here is the least common multiple of the leading monomials of F and G. In this case, that least common multiple is x squared y. And so the S polynomial of F and G is x squared y divided by the leading term of F, in this case x squared, multiplied by F minus x squared y over xy multiplied by G. This is precisely what needs to be multiplied by F so that the leading terms cancel. So this is multiplying F by y and multiplying G by X. So we're gonna get cancellation on the leading terms, and we're gonna get this, the rest. So y times F squared, F would get us yx squared, and then here we're going to get x squared y, and we're going to get the leading terms canceled. And so what we get is just the rest of it, which is y cubed plus y plus x squared minus xy. So these S polynomials are very interesting because of this theorem. This is called Buchberger's criterion, and it's due to Buchberger. It says that if Isa is the ideal generated by a G1 through GT, G is a Groebner basis if and only if for every two indices I different from J, the remainder of division of the S polynomial of Gi and Gj by G is 0. So if and only if for every S polynomial of a pair of polynomials in G, the remainder of dividing that S polynomial by G is 0. And the importance of this is that it gives us a finite set of tests we can do to verify that this thing is a Groebner basis. So if you look back at the definition of a Groebner basis, this is on the right-hand side, we have an infinite set, and we don't have a way to test that something is a Groebner basis. We cannot take every single element in the ideal generated by the leading terms of the ideal and see if it's generated by the leading terms of the GIs. But what Buchberger did was to come up with a way to test this in a finite set. So this S polynomials is like a critical set of polynomials, a finite and enough group of polynomials. And they are going to be important later in many ways, because what we're going to see is that they are really a basis for the module syzygies. And this is, you can work with any basis for the module syzygies. That's enough. And also for computation, it's going to be important because if you get a smaller basis for the module of syzygies, you can perhaps compute the Groebner basis faster. Right? So this one is not the best one. It's one basis, but it could be you can get a smaller one and have a faster way to check if you have a Groebner base. All right. So let's prove that let's prove this theory. Let's start with a small case. This is like a lemma that is going to show us that this is really a basis for the module of syzygies in a certain sense, or at least as a vector space over K in certain cases. So this is like a simple way to show this. So let me state this lemma. F the sum sub i's into S with the A sub i's in the field and of multi-degree the same multi-degree. So every one of the polynomials of the same multi-degree, say delta. If there's cancellation here, if we get any cancellation here, so if there's a drop in multi-degree, if the multi-degree F is strictly less than the multi-degree of the F sub i's, then that F can be written in terms of the S polynomials. That F can be written as a sum where the Bij's are in the field. This is, let's say, I less than J, so that we get all the S polynomials. So if there's a drop, if there's a cancellation happening on this combination here, on this linear combination, at the top, on the leading terms, then the whole sum can be written in terms of the S polynomials. In a sense, here the S polynomials generate all the possible cancellations. Something like that is really what's happening. It's a set of generators, in a sense. But we will talk later about the module of syzygies. All right. So to prove this, so I equal to the leading coefficient of F sub I. Note that since there's cancellation happening on the leading terms, then the sum of the A sub i's multiplied by these leading coefficients is equal to 0, since I equals 1 to S. Also, note that since all the F sub i's have the same multi-degree, then the S polynomials are very simple. The S polynomial of Fi Fj simply get multiplied by the correct coefficient. So it's simply it turns out to be something like f sub I over d sub I minus f sub j is j. So we're making them coincide, the leading term. So perhaps we can give this a name. They're going to show up later. Call these p sub I and p sub j. And then now let's take the f. Let's rewrite it in terms of base. This is going to be some of this. And then you get, I want the di's to be out there. And then you get something like f sub I over d sub I. So this is p sub I. I just extracted the leading coefficient so that I get these monic polynomials out there on the clear. And then you can write this as a telescoping sum so that we get the S polynomials out there. And I'm going to write it so that it is evident that it happens. So you get A1 D1 times P1 minus P2 plus A1 D1 minus plus A2 D2 2 minus P3 plus dot 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 plus 1 D1 to A S minus 1 S minus 1 multiplied by P S minus 1 minus PS. And then there's the last one, which is A1 D1 plus up to AS DS. But then we don't have PS. And one can convince oneself that should convince yourself that this is actually true, that this can be written in this way, but it's not hard to see it. Here you have A1 D1 P1, which is the first term of this sum. Then we get A1 D1 multiplied by minus P2. But then that one cancels with A1 D1 P2 here. Next, we get A2 D2 P2 here, and which is in the sum. And then the other ones, the ones that go with P3, get canceled with A1 D1 with the next one. So the things get canceled, we're only left with this here. So you go through it carefully, you can see that it does work. At the end, in the last one, PS multiplied by this cancels with PS multiplied by all the positive, the first s minus 1 terms here, and at the end you get as, ds, ps, the last one. That's work. But it also gives us something very nice, which is this here is 0, and we're left with something of the form that we wanted. These coefficients here are just elements in the field. We're multiplying elements in the field, we get elements in the field. So these are what we're going to call Bij, and then these Pi minus Pj's are the S polynomials. In fact, you don't even need all of them. In this case, we only needed a few. So this is j equals to I plus 1. So this is, say, I plus 1 from 1 to s minus 1. Which also hints us that this basis for the syzygies is much more than you actually need. But okay, we got the result. We got the lemma. And using that lemma, we can prove the theorem. I have 10 minutes. I hope I can go through this in the next 10 minutes. This I'll give the ideas of how to both use this lemma to prove it.
Sir, hello.
Yes.
Sir, can you explain what is the leading coefficient of Fi?
Yes. Yes. The leading coefficient of Fi is the field element that is multiplying the leading monomial. So if you have, I don't know, 3x squared minus 2xy plus 3, the leading term is 3x squared. The leading monomial is x squared. And the leading coefficient is just the 3. So it's the coefficient in the leading term.
Okay, and then why on the second row from the proof part, note that the summation of AIDI equal to 0.
Oh, good.
Not
This one here.
yes.
Right. So this condition here, together with this condition here, what it's telling us is that all the f sub i's have the same leading monomial, but they may have different leading coefficients. Now, if we say that the multi-degree of f is less than delta, we're saying that the leading term of f is less than the leading term of any of the f sub i's. So what is happening is that the leading terms of the f sub i's are being cancelled. There's a cancellation happening on the leading terms of the f sub i's. So if we look at the leading coefficients here, there must be cancellation, and that's exactly this. The leading coefficients of the f sub i's with the a sub i's cancel.
Maybe can you give any example for that?
Yes, I can try. So we're talking about polynomials with the same leading monomial. So it can be something like 3x squared minus ta ta ta, and another one like I don't know, 4x squared plus 2x or something. And these have the same leading monomial, delta. I mean, it's not delta, it's x to the delta, it's x squared, the same leading monomial. And this condition here says that there's a combination of them that cancels the leading monomials. So we get something like A1 times the first one A1 times the first one plus A2 times the second one equals to some f. But the leading monomial of f is strictly less than the leading monomial of the f sub i's. So what it's saying, that what condition is saying is that when you do this combination, the leading monomial of f is less than x squared. Therefore, if you look at just what's happening on the leading terms, you're getting A1 times 3 plus A2 times 4 vanishing. This must vanish so that x squared is not happening in f. There's no x squared in f. That's that condition there.
Okay, thank you, sir.
Thank you for the question. All right. So let's see. Where does this leaves us? With 5 minutes to prove. You say. Should we call it?
I think we can also prove it. I mean, take 5 minutes more, but I mean, not much more than that.
Let's try to do it in 5 minutes. Maybe that's a good idea. Even if I don't show all the details, maybe I'll give at least the idea of how to prove it. Without, I'm going to sketch a proof.
As I said, it can take 5 minutes more. But
and we started 5 minutes late, so I think it's all right. So there's one direction that it's immediate. So if G is a Groebner basis, we get that all of these go to 0. What is interesting is the other direction. So we're interested in this direction. So we are assuming that that all S polynomials reduced to 0 under division by G. I'm going to write that like this. When you divide by G, you get 0. All of them go to 0. right? And we want to show that this is a, but under that condition, G is a Groebner basis. Remember that a Groebner basis, we're going to use the definition, and that's that all the leading terms generate the leading terms of the whole idea. So let's take an element, an arbitrary element to the idea. And we're going to show that there's some leading term of some GI that divides the leading term of F. So what we want to show is that there's some leading term of some GI that divides the leading term of an arbitrary F in the idea. That's what we want to show. Now, since F is in the ideal, we can, yes, and the ideal is generated by G1 through GT. So we can write it in terms of the GIs. So for some HIs, but we're going to do something more. We're going to, there could be many such ways to write F as a combination of the GIs. But I want one that is minimal in the multi-degree of these products. So I want to choose the H sub i's so that they have minimal multi-degree well, actually, it must be of the maximum because there are several there. So I need that to be of the maximum of the multi-degrees that happen there. The max multi-degree of the HI. And yes, because it's a monomial order, it's a well order, we can do that. We can choose. We can assume that the HIs are ones that have minimal max multi-degree. Now, if the multi-degree, if this max multi-degree, which I should give it a name, I think I'm going to be using that a lot. Delta. So if this max multi-degree of the HIs GIs is equal to the multi-degree of F, we're done. Because that means that there's some leading term of GI that divides the leading terms of F. So the interesting case is when this is larger, when there's cancellation happening. So should I call this delta? I'm not sure. If the multi-degree is equal to delta, we're done. reason is because some leading term of GI divides the leading term of F. So what is interesting is, let's suppose that delta is strictly less. It is the other way, that the multi-degree F is strictly less than delta. So there's some cancellation happening among the HIs, GIs. So here's what we do. Take F. We're going to isolate that cancellation in the top. So we can look at only those in which the multi-degree, which I'm gonna give it a name, M of I, is exactly delta, and the ones that are less than delta. So I'm gonna isolate the cancellation so that I can apply the lemma, right? But I need a little bit more than that to isolate the lemma. So I'm going to take just the leading terms of the HIs. And I'm going to leave the rest behind because all of the other things have less multi-degree. So here we have the rest, which is F minus the leading term of, HI minus the leading term of HI times GI. And then we have also the rest. So HI, GI, but with a multi-degree is strictly less than delta. So what we're doing is we're isolating the part of the sum that has exactly multi-degree delta. And because this one is, as in the lemma, just coefficients multiplied by polynomials of the same multi-degree, we can apply the lemma here and express this in terms of the S polynomials. We express this as a combination of the S polynomials. Since we have little time, I'm just going to tell you what happens next. So then the idea is you apply the lemma here. This is where the cancellation is happening. You get this in terms of the S polynomials. Then you apply the hypothesis. The S polynomials are divisible by G. So you express each one of the S polynomials in terms of the basis using the division algorithm. And the division algorithm is nice because it only goes down in multi-degree. You're never going up in multi-degree. This is a division where you're going down in multi-degree. So you guarantee that expression that comes from the S polynomials goes down in multi-degree. And eventually you get to the GIs, to the original GIs. And so what happens here is that you transform this expression into an expression on a lower multi-degree by going down these polynomials and then expressing that in terms of the basis G. And that contradicts the minimality of the choice you made for the H slice. Steady? And I'm gonna leave it there for now, for today, because it's getting late already. We're tired. Can continue tomorrow. Thanks a lot. Thanks for coming, and I'll see you tomorrow